So I'm going to introduce a little bit of introductory chemistry to go along with our cell biology. This is to make sure that we understand the chemical basis of the molecules that make up our cells. Biology and chemistry are, of course, intertwined because all of life is made up of matter, and matter are the elements that we're going to describe in this chapter. We'll spend a lot of time talking about water. This will mostly be in next week's lesson. Matter is anything that takes up space and has mass. Of course, we're going to be talking about specific components of matter known as atoms. The four key elements found in living things are carbon, hydrogen, oxygen, and nitrogen. And then there are, of course, several others. So those four make up 96% of living matter. Essential elements are anything an organism needs to complete its life cycle. They vary from plants to animals, and even within animals, different elements are essential. Others can be synthesized by or are not essential, or compounds that can be synthesized by the organism. Trace elements may be essential, but they're just required in much smaller quantities than those elements that are found abundantly in living things. Compounds are two or more elements in a fixed ratio, and compounds have what we call emergent properties. Other things also have emergent properties, but compounds like water have properties that neither hydrogen or oxygen have on their own. So remember, emergent properties are the properties that are found by subunits in a specific orientation. And that's true for water the same way that it's true for a bicycle. Sodium chloride is a compound. It has some properties as a salt that neither sodium nor chlorine have on their own. So another example of emergent properties. These are some of the elements found in living things, in humans specifically, and their proportions. I, of course, wouldn't ask you to reproduce any of these numbers, but you should know these four guys are the most abundant elements in us. You can remember this. We're a carbon-based life form. We're mostly made of water, and then throw in some sodium. Oops, sorry, nitrogen, not sodium. Nitrogen in addition. Here are some of the less abundant elements, but things you might recognize that we would have, like magnesium, chloride, sodium, sulfur, and then things like iron, fluorine we have in very small quantities. So we're going to briefly go over atomic structure, and from there go into what makes an atom reactive. So remember, atoms have three subatomic particles: protons, neutrons, and electrons. Here's a model of an atom. Here's the atomic nucleus. It has protons and neutrons in the atomic nucleus. Protons have a positive charge. Neutrons have a neutral charge, hence the name. And both of these have mass. Individually, they have one atomic mass unit each, which is also known as a Dalton. They're found in the atomic nucleus. In an orbital around the atomic nucleus, sometimes also referred to as an electron cloud, we'll talk about electron shells, are electrons. Electrons have a negative charge and negligible mass. And the electron shells around or orbitals around the atomic nucleus help determine the reactivity of an atom. So we'll come back to those. This particular atom is helium. We know it's helium because it has two protons. Anything with two protons is an atom of helium. And then it's a neutral atom because it has two positively charged protons and two negatively charged electrons. So the positive and negative charges balance out, and it's neutral. Most atoms are going to have the same number of neutrons as they have protons, but not all. And so we'll see there are some variations or differences in the number of neutrons that might be present. This happens to be an atom of helium. So how do we know what element is what? How are the elements distinguished from one another? It's the number of protons, which is also known as the atomic mass, atomic number, excuse me. determines the identity of an atom. So if it has 2 protons, it's helium. It's always going to be helium if it has 2 protons. On a periodic table, you'll see some numbers that look like this. Here's for sodium. The number 11 is the atomic number, which is the number of protons. Determines the identity of the atom. And then if it's a neutral atom of sodium, it's going to have 11 electrons as well. The number at the top here is the mass number, which is the number of protons plus the number of neutrons. And so for this particular element, there are 12 neutrons rather than 11, even though there are 11 protons. So we estimate the total mass then to be about 23 daltons, since each of the protons and neutrons has about 1 atomic mass unit. So when you look at a periodic table, you can see those same characteristics. Here's helium, the one we were talking about a minute ago. Here's the atomic number 2, that's the number of protons. Here's the symbol, helium. And then the number below, 4.0026, is the average atomic mass. And so this means that most atoms of helium have 4 atomic mass units, or 4 daltons of mass, meaning 2 protons and 2 neutrons. There are a few atoms of helium that have more than 2 neutrons, so that this number is slightly bigger than 4. If we look at carbon, we see carbon has 6 protons. A neutral atom of carbon would have 6 electrons. And the atomic mass or mass number is about 12, so that means it usually has 6 neutrons as well, but occasionally can have more than 6. The other thing you can learn from the periodic table is that if they're in the same column on the periodic table, they have similar chemical characteristics. And we'll get that information again in a minute, because we're going to see what the electron distribution looks like. And so the columns on the periodic table share common electron distributions. Isotopes are elements of an atom that have a different number of neutrons, so they differ in the number of neutrons. So for instance, there's an isotope of carbon known as carbon-14. We just saw that carbon is normally a mass of 12, so this one has 6 protons and 6 neutrons. Carbon-14 has 6 protons because it's an atom of carbon, but it has 8 neutrons. So it differs in the number of neutrons. And carbon-14 happens to be a radioactive isotope, which means it's unstable. And as it decays, it gives off energy that can be detected. That's what radioactivity is. So radioactive isotopes are unstable isotopes. Here, radioactive iodine is being used to label the thyroid gland. So radioactive isotopes are used in tracing experiments frequently in biology. And they can be used in some medical treatments as well. My mom had thyroid cancer, and so she had a large dose of radioactive iodine to help ablate the cancer cells in her thyroid. Iodine happens to accumulate in your thyroid gland. So let's talk about those electron shells and the state of electrons in the electron shells. So I mentioned before that the first electron shell holds, maybe I didn't mention this, holds 2 electrons, and then the second and third shells each hold 8 electrons. And the electrons that are close to the atomic nucleus are low energy electrons, so kind of like this ball near the bottom of the stairs. As the electrons move away from the atomic nucleus, they're at a higher state of energy. So this is known as potential energy, as I'll say in a minute. It's energy due to position or location. So like a ball at the top of the stairs, these have energy that can be released as they move towards the bottom of the stairs. Or water behind a dam is another example of potential energy. So electrons can move from this low energy state at the bottom of the stairs out to a higher energy state. Energy has to be added for that to happen. And they can also move from this higher energy state to a lower energy state if they move closer to an atomic nucleus. And when that happens, they release energy. So we'll go through this in a lot more detail in our cellular respiration and photosynthesis chapters. But essentially, life is just an electron looking for a place to land. And so photosynthesis moves electrons away from an atomic nucleus, and cellular respiration moves electrons back. So Electrons that are closer to the atomic nucleus have less energy, away from have higher energy. Energy is capacity to do work. And potential energy is energy due to position or location, like that ball at the top of the stairs. And so electrons have potential energy due to their distance from the atomic nucleus. So if we go back to the periodic table, from the periodic table, we can predict what the electron distribution of an element is as well for a neutral atom. So here, if we look at helium, the atomic number is 2, so that means it has 2 protons. And if it's a neutral atom, it also has 2 electrons. So if we're going to draw the electron distribution of helium, we're going to put 2 electrons in this first electron shell. And that now is full because the first electron shell only holds 2 electrons. Let's draw the electron distribution of carbon. Carbon has an atomic number of 6. That means it has 6 protons and 6 electrons. So the first 2 electrons are going to go in the first electron shell, and then you're going to have 4 electrons in the second shell. Now the second shell holds a maximum of 8 electrons. So carbon has room for 4 more electrons. This is known as its valence. How many electrons does it need to fill its outer shell? And as we'll see in a moment, elements are going to engage in chemical reactions, form covalent bonds to fill their outer shells or their valence shells. So here we see hydrogen. Hydrogen has 1 proton in its atomic nucleus and 1 electron in its electron shell. Because that first electron shell can hold 2, it has 1 space to fill. So what hydrogen is going to do is go and find another atom to share electrons with in order to fill its outer shell. One of the most common ways you'll see hydrogen do this is with another hydrogen atom. So 2 hydrogen atoms will get together. They'll each bring 1 electron, and they'll share that electron between them. So now they have 2 electrons that are being shared between these 2 hydrogen atoms. And both of the hydrogen atoms can count those 2 electrons in their valence shell. Now their valence or outer shell is full, and they're stable as hydrogen gas. So hydrogen gas in the atmosphere is found as H2, which is another way to represent this, with these 2 hydrogen atoms sharing this pair of valence electrons. That sharing is called a covalent bond, which is share a pair of valence electrons. The second shell can hold up to 8 electrons. This is neon. It has 8 electrons in its outer shell. It doesn't have any spaces to fill, so it's stable. So just like helium, the electron shell of this atom is completely full already, so it's non-reactive because it doesn't need to fill its electron shell. So in the very right-hand side of the periodic table are all those stable non-reactive elements, also known as the noble gases, that don't react with other elements. So I want you to go ahead and draw the electron distribution of these elements because we're going to see how they get together and share electrons with other elements. So these are going to be the important ones to know. And the chemical behavior of these elements determined by their valence shell. So it's based on their number of electrons, and you can draw their electron distributions if you know the number of electrons. So oxygen, for instance, has an atomic number of 8, so it's going to have 2 electrons in its first shell, and then 6 electrons in its outer shell. It has a valence of 2, which means it needs to share or make covalent bonds with other elements to fill those last 2 spaces in its valence shell. So draw the electron distribution of those and then determine their valence. We've said already the valence of carbon was 4, it has 4 spaces to fill. The valence of oxygen is 2. If you think back to hydrogen, it had 1 electron, 1 space to fill, so its valence is 1. And then I'll go ahead and tell you that nitrogen's valence is 3, but draw that out and make sure that that makes sense to you. So here you can see the electron distribution. Here are those noble gases I mentioned that have completely full outer shells, and so they don't react with other elements. And then here's hydrogen with its one shell, here's carbon. Another thing to notice is that the outer shells of the elements in the same column are going to be the same. So if we look at carbon versus silicon, silicon also has 4 spaces to fill, so it's going to have a chemical property similar to carbon. And same thing, oxygen versus sulfur are going to have similar properties. So what is a covalent bond? It is sharing a pair of valence electrons, and the absence of complete valence shells determines an element's reactivity. There are spaces to fill in the outer shell, then that element is going to interact with other elements, form chemical bonds or covalent bonds with other elements to fill their outer shell. So here's the covalent bond between the 2 hydrogen atoms I mentioned earlier. This is a couple of other ways to represent that bond. So most often we're going to just use a dash between the 2 letters, but you can think of that also as 2 dots. That Lewis dot structure sort of represents those 2 shared electrons between the 2 elements. You can have double or even triple covalent bonds where more than 1 pair of valence electrons are shared. So these 2 oxygen atoms are sharing 2 pairs of valence electrons, and nitrogen gas can actually share 3 pairs of valence electrons. So be sure to be able to write out and draw the organization, a Lewis dot structure of some common compounds. So let's look at water for a second. We said water has 2 spaces to fill and hydrogen has 1 space to fill. So a water molecule is going to have a covalent bond between oxygen and two covalent bonds between oxygen and 2 hydrogens. So this hydrogen now gets to share these 2 electrons. Its outer shell is full. This one gets to share these 2 electrons, and then oxygen can count those 2 pairs of shared electrons in its total of 8, and its outer shell is also full. Here are some drawings of a little bit better drawing of water, what I just showed you. And here's another compound that I asked you to represent on the previous page, methanol. So next week we'll talk more about covalent bonds and talk about what makes them polar versus not polar. But for this week, make sure you're comfortable with atomic structure and also that you recognize how many covalent bonds or what the valence is of these common elements.